So I'll say 2 sentences and then we'll kick it off right away. So we'll be hearing about a new development out of a research course that I direct at Georgia Tech. It's a vertically integrated project, and so we have a couple students that do very different things. As some of them do independent studies, some of them do capstones, and some of them just regularly take this class. And so they all found themselves working on a Grasshopper, I guess, implementation or plugin development effort around a microclimate simulation solver that came out of ETH-Zurich. And I think this has started, Gonzalo, remind me, maybe in June, I think with your internship at Princeton Will. And so we took this further, and Shruti and Chinmay joined. They wanted to do capstone projects on slightly related issues. And then Marcelo, who joined Georgia Tech, joined the VIP course and helped with some of that development. And there's Ray. I don't know if he's going to be joining today, but he also helped. I do want to acknowledge his work as well. But I think he took the course for 0 credits and just audited. So we'll see if he's joining. But yeah, so they did this work. Perkins and Will, as a sort of research partner, Tyrone here on the call is a employee with Perkins and Will. I believe, is it research or is it just Perkins and Will generally?
It's Perkins and Will, but also under research as well.
Also under research. And so there's an interest there to obviously try out this development on real world projects to actually solve some problems that are occurring on a daily basis. And so we welcome their feedback, and we of course are inspired by some of the actual problems that they see on a daily basis. And so yeah, I'll keep quiet from here. There's Timur joining. And then Gonzalo, are you directing the slides? I'll just hand it over to you. So we're recording already, and then you can just take it away.
Okay, thank you, Patrick. Do you see the slides?
Yes, we can see the screen. Thank you.
Okay. Good day, everyone. So we're part of this team called Microclimate-UMCF. UMCF coming from the Open Microclimate Foam Solver. Our full team is quite large, so we have Patrick leading here this effort. Me, Gonzalo, in charge of the main development of the plugin architecture. Marcelo here is also supporting that effort and working also some of the testing of the plugin. Chinmay is working primarily in the vegetation parameters. Shruti designing some case studies so we can run this on. Sina is not here, I believe. He was supporting us on the technical side, the validation. And Ray, who's also not here, he supported us in some testing, some fixing some bugs, and some general technical problem solving things. Like Patrick said, this is starting Perkins and Will as an internship when I started the development of this. And also seniors from the Toronto Metropolitan University, so it's in a way it's like a partner. I will be talking primarily about Metafoam, which is this platform that we designed to, in broad terms, facilitate the implementation of Grasshopper plugins based on OpenFOAM cases. So the Metafoam platform has like three steps I want to talk about. The first one is the class library, which contains like some methods and to parse and modify OpenFOAM cases. The second, we had like a very simple, we could call it an app, a console app. It's just like the process to actually take a case from OpenFOAM and serialize into JSON files that we can later read. And there's the actual Grasshopper plugin itself, which we could say is like one instance of application of this Metafoam platform. In this case, for the Open Microclimate Foam to run microclimate simulations in Grasshopper. So the main, like one of the main reasons we're doing this whole Metafoam thing is that OpenFOAM is the main limitation, we could say, from a user perspective of OpenFOAM is the interface, like a structure in a dozens of files, which are like distributed like multiple folders. Even more if we talk about like a multi-region cases that we're looking at right now. And also each file is text, and when you open, you will see like a wide number of parameters that needs to be modified one by one in the text editor, which makes it very difficult for people like me, like architects, to actually deal with. It's not very intuitive and it's not very simple to use. So of course the open form files for like a specific syntax, like mostly like dictionaries and lists, and these ones are like a nested between each other in several levels. So that what we're trying to do then with this the first like big task here is to provide like some kind of generic open form file modifier that we can use, and we can leverage that to actually build the grasshopper plugin on top of that. So the steps here involved are, first we have we need to parse all these files from the open form case, and we store them as a C# dictionary as file containers. The main reason to use C# is just because it's like a good language to build grasshopper plugins. We organize these file containers into directory containers so as to match the structure of the regions and the cases in OpenFOAM. It also allows the modification and the addition of multiple regions with more flexibility. And then we customize these dictionaries by adding or moving entries to this, which is a specific class I will explain in a while. And then we will, after modification, we print it back in as text files, and then we can recreate a new case to run a simulation. The overall structure of all these steps is organized in this diagram, starting from the bottom. You have the development of the actual Metaform class library. It's ends up giving you like a DLL. And apparently we have the Metaform app, just when you select the case you want to parse. And after having that like serialized into a JSON, we can then use, a developer can come in and use all these methods and routine classes to actually write their own like a Grasshopper plugin based on the files that were parsed. And at the end of on the top, you can see the actual user just using text, taking their geometry and Rhino set up the simulation, and they just run the simulation. So the first one, the Metaform class library, is the class diagram. The first step here is these three classes that are used. The purpose is to just allocate or contain multiple files. Directory containers, the more basic abstract class that are used by the case in the region. This one only provides like some functionality to get file containers. The region itself is pointing to like a specific open form region, such as air, buildings, or vegetation. This one stores like all the files particular to that region. It has also some logic that can be used later on by a user, can be filled with a user to actually modify the files the way they want. And the case itself is just a collection of multiple regions. It also contains all the files that do not belong to any regions, which are primarily for the global type of settings of the simulation. The file container is like our main class probably here. It's an abstract class. It contains like the address of the file and the content as a C# dictionary. And this dictionary is a nested dictionary of a string and object. There's like 4 types of them. So we have the dictionary container, the kind of generic one that contains most settings and the initial conditions of an OpenFOAM file. The list container has like weather-related information, which is usually time-based. It's a way more simple. The text container is like a generic container for anything that's text-based that doesn't follow necessarily the OpenFOAM syntax. And the mesh container is actually just carry the geometry you will be modifying in Rhino. Then to modify, we have this. To modify files, we have this whole structure here. We have a setting which is just like a collection of multiple entries, and entries are the main like instances that carry all the specification for a file modification. And they're self-contained, so the idea is that we want to be able to modify any file in any place, disregarding of in which part of Grasshopper you will be, for example. So in this case, the address contains like the full relative path to the case of the file, and the enter key in this case is that the name of the dictionary, the nested dictionary, is one after the other to reach the value that you actually want to change. Then for the metaphor,
Can I just say one thing real quick? Maybe
yeah.
could you add 2 sentences of why we went through this detour. You know, most people when they do something like this, they just do a Grasshopper plugin and call it a day. And we spend, you know, maybe an additional 4 to 8 weeks to sort of really think about how this could be flexibly carried forward into the future. Maybe you can just make an example of why this is important, especially specifically with OpenFOAM. I think for the audience that would be helpful. Yeah.
Yeah, and so I would say that probably one big limitation that we have been facing the part with Eddie is that it's very difficult to add new features every time there's like an update, or you wanna add like different setting, or you wanna add a different, or you have multiple regions, you wanna add like the same copy of a region. It's very difficult to then come in and modify the whole structure to make it work. My understanding is right now in Eddie, like the way you modify the text is like very like ad hoc. But in this way, we have like an underlying, like a foundation that we can more quickly, way more flexible way, modify files in whatever way we want. So in this case, we can take like a raw OpenFOAM case, any type of case, and then quickly convert that into, or it gives you like a set of tools that you can quickly use to create like your own plugin. So in that case, every time there's like a new version coming, or especially in this case, because this particular plugin we're aiming for, based on the solver, the Oreo Microclimate-UMCF solver is quite new, or it's been like it's constantly being updated. So every time they make a new version, we wanna have a way to quickly take that version and create an update everything in a more streamlined way. That way, is like the main reason, one of the main reasons behind this. Also for the flexibility of having not only this particular solver they want to try to implement, we're trying to implement more like we want the ability to have multiple types of cases to be taken into their own plugin eventually. Yeah. So for the app, it's just a very simple console app. You just take an input. In this case, you define the input what your case is. Will be any type of OpenFOAM case. It is gonna just read, parse, and serialize all the files inside as a JSON file, and it's gonna give you a structure like that for each region. So we have, in this case of the UMCF, we have the air region, the buildings region, the vegetation, and here in the case we have all the global type of files that don't belong to any type of region, and these are then stored and compiled with the Metafoam assembly. The important part here is that we want to keep not only the content of the file, but also the address in the format that we use to then be able to write the file back to the original location. You want to keep also the type of the file, so we can like read as the class that they belong to. And finally, the actual Grasshopper plugin to run on microclimate simulations, UMCF. This one is the same diagram, but now the main difference that the developer come in and they inherit some from the existing classes from the case, the UMCF class, and from the region we have the air, the building, and vegetation. So they come in, they just take the existing library and they add any type of methods they need to make this thing work. So the UMCF one just contains all the file containers. In this case, we have these 3 type of regions: air region, the building, and the vegetation, like I said before. And each one have their own specific requirements. So the air region in this case contains also all the information about the simulation domain, including like the direction of the wind and the parameters to define like the box. And the building and the vegetation region, they contain a mesh with the geometry required to run the simulation. In addition, they also like override the process entries method. This is called on the case, which contains all the file modifications that are like collected through Grasshopper inputs. So the overall features of this plugin is that you input like the geometry of buildings and vegetations, you define a wind speed, direction, building material, and vegetation properties together with a weather file, the start day, start time, and duration, and this will output the per hour, the temperature, the absolute humidity, wind velocity, and the pressure. The main relevant ones. There's like more, of course. In the Grasshopper definition, look like this. We'll go like one by one here. Here on the top, we have the air. We have the the ideal condition with the wind speed, the higher this happens, the direction of the wind, and here we have the box domain. It's just define the dimensions of the simulation domain, and important one, the cell size of the simulation. For the buildings, you have the actual geometry of the building, the material of the building you're going to use, and parameters defining the refinement of the meshing. And similar way for the vegetation, you have a specific input for the LED, liquid density, array of vegetation properties that Jimmy will be talking more about, and then similar settings for the vegetation mesh. And then finally for the timing, you put a weather file, which is right here, and then you define the start day, start time, and duration, and this will then collect all the information of the weather that we need to actually run the simulation. We also have, of course, several run settings. The main one we're using here is just the number of CPUs that we're gonna run this in parallel, and this is the max flow iteration. Is just we modify this to make the make the simulation faster when we're testing or not. And then we have the component that takes everything together, the case. And this has like an input to here to just write the case and to clear it. And you can also specify the name of the case and the working directory where this will be written. And then you can just run the case. You can have some options to run this in parallel single. First, prepare to get the meshing and then the running simulation itself. And almost at the end here, we have the probing. So after the simulation runs, you can specify which of the fields that you want to get from the simulation. Pretty much the name of the probing itself, which requires like a set of inputs. You can, any kind of inputs will a set of points to get the probing for. And after that, after you run the probing, you can use like a get probe components. Will output like a one for each hour. Will output like all the values for each point. And these are just vanilla components from Grasshopper here for visualization, which allow you to just see the results indirectly on Grasshopper, and you get like some quick example, some of the give an animation of the results of the temperature and the wind velocity. But so we'll see more of this from Gmail later on. And that was it from me. Now Marcelo will take it with the next part.
Hi, can you hear me?
Yeah.
Yes, Marcelo, let me say one sentence for the ones that join later. So Gonzalo led this project, came out of his internship at Perkins & Will, and there were 4 more students that investigated sub-issues or sub-problems related to this development as it pertains to meshing, vegetation, canonical test cases, and what am I forgetting? Is that it? And of course, Marcelo, which we're going to hear about right now. So yeah, please continue.
Okay, my work during the semester was two-sided. The first part was to add and develop additional features for the UMCF plugin for Grasshopper, mainly focused on visualization. Just because before that we needed to rely on some viewers like ParaView, for example, and it will be like a good feature to have to actually some sort of quick visualization and further manipulation of the geometry meshes from the simulation domain results to the Grasshopper environment. So go next slide, please. And just keep going, so it will be like really fast. The first thing is that there is an object, kind of, called polymesh that contains all the information related to the point, faces, and cells for the mesh composition of the OpenFOAM geometry, related to the air region, the vegetation region, and the building regions, or maybe like the solid region, more genetic way. But so the basic workflow is to retrieve all the global mesh using the point and faces. That is a relationship of numbers between them to actually construct the faces, and then the additional feature to actually retrieve a specific region. In this case, that we see here in the image in the picture is for the vegetation region, the array of cells that are set for the specific setting. So then we did a further optimization because the initial version was just an individual mesh for each cell, but then that was, since a lot of these geometries have a lot of cells, a high amount of cells, we were actually able to create like a single mesh based on the information. So it works a lot more faster and allows you to do further processing in the Grasshopper environment. And finally, since the plugin started to have more updated releases like to be used, we integrated this to the UMCF case class to actually work and be fully integrated in the whole workflow of the process. This is another feature that we work during the course of the semester. That is the need of what could we handle more complex topography geometries based on a custom input for a surface, a B-rep or even a mesh that is not flat. So this is a component based on Professor Kastner kind of vanilla Grasshopper implementation, but we aim to build a more compact, more integrated solution into the whole framework and workflow of the plugin. And then we need to do more testing, basically initially on the performance and trying to solve all the individual errors that were some related to memory issues and other to geometry issues, geometrical things. So I was in charge of studying and finding some relevant insights on the geometry of the trees. And for this one, to begin with, I chose a small sample of trees with a pretty generic and arbitrary building geometry and performed a fractional design of experiments with a size of 16 to actually get the initial data sets that we can try to find some observation from it, so we can really understand how to actually build proper meshes geometry for the trees. That was the main issue. So there are a lot of parameters related to the mesh quality, the functions that OpenFOAM handle to actually build meshes, as the snappy HexMesh dictionary and castellated mesh controls. But based on that, go next, please. Yeah. We basically rely on the check mesh function that basically tell us if a mesh is good or is not good. So if it's good, the simulation is more prone to run successfully, right? So the geometry has an overall healthy status. This is the results of the fractional design of experience that we performed trying to using the shrink wrap method from Grasshopper to build a single mesh that contains all the three geometries, and we can see there are more, well, for the max skewness, the acceptable values is up to 4.0 and max non-orthogonality is around 75, I think, that we define that way. But the values are really close, but the check mesh says all the keep scrolling through the next slides. All these results are qualified as good meshes using the check mesh function. So probably that we needed to do further testing to actually make this run in a consistent way. And then we ran to another hypothesis that this is another functionality that we developed for the plugin to visualize the sets that were created when the check mesh function outputs some bad geometries. For example, low quality tetrahedron faces or faces with cells with too large skewness values. So we started to think about it, and we noticed that there are some problematic edges on mesh geometries for trees in this case. So we did the following. We manually modified the files for that tells the solver how to render, so how to generate the meshes, and we delete any process that involves the trees or the geometries to actually have edges. And by doing that, we were able to run simulation more consistently based on the formula from the chipad, way of generating meshes and avoiding problematic edges on the. So then we started doing a benchmark process to actually, this was, please know that this was all run on my own end. Then we started using a powerful server. So we started to avoid the problem, the memory problems during simulation with large geometries. But we found from this that modifying the refinement levels by one value, by lowering one value, the amount of total cells in the simulations decreases drastically, but it doesn't really have an impact on if the simulation will successfully run or fail. So this is more tied to the overall domain size domain. So and in the end, we started to run, since the plugin was more robust to actually work, and we started to do further testing. We were actually needed to see if the temperature values were actually working, and we get some conclusions based on this. So we choose a EPW file that is from Calama, Chile, that is a desert-like weather. So we started to see what kind of configuration or setting do we need to actually have significant changes in temperature values around, under, or next to the vegetation geometries. So using this generic and default settings, we were not getting any much differences. Maybe because the simulation domain is too small, it needs to be more large or enter a steady state to actually represent and give more consistent results. But then we tried to see, okay, is the solver actually doing its job? And we set a completely out of scale LED value of 100. Of course, Chinmay will explain this more in depth, but we were able to get the temperature differences more significantly around the trees. So this is expected behavior, but obviously with a smaller LED value. And also you can, of course, go to the GitHub repository. You can find the documentation of this plugin, from the installation to all the features that Gonzalo mentions and described previously, with more features. And this will be constantly updated using of course, in the process, we continue to do more releases of this one. And that's for my part. Thank you.
Right. Jimmy, before you jump in, we have one question. Maybe we can take two questions, actually. Maybe Gonzalo can take just half a minute to address these before we forget what these are all about. We're moving into applications now. Also, this can be maybe one sentence. Where can this also be downloaded? It's on the package manager still, right? Is that still the case?
Yeah, that is the case, yes.
Okay.
If you type UMCF on the package manager right now, you should see it in the plugin.
Yeah, so we have one question for Gonzalo, one for Marcelo. Maybe while we're on these topics, maybe you can quickly address them in the chat.
Answering Tyrone's questions for me.
Maybe repeat the question real quick in one half a sentence. Yeah, since this is recorded.
I mean, the question is, could you share your thoughts on the technological level of the plugin and the necessity for its expansion? usually expansion is needed, what limitations have you identified in this work, and what area should we focus for next steps? We suggest many. So I'm not sure what you mean with technological level, but I would say maybe you mean like a in depth, like a in technicality. I think the probably next step in the sense of the metaphone side will be to make it easier to modify files. Because right now you have to what we actually need is like a custom container class. Right now we're using like a generic dictionary, but ideally we need like a form dictionary. I call it formunary. And this will make it even easier to actually modify files in a more intuitive way. Well, also I would like to add like some like autocomplete kind of thing in there, so you can like every time you have a file container, you can see what's already inside. That might be more complicated to. I'm not sure if that how difficult that will be implemented. Not on the metaphone side. On the actual plugin side, there are many things we still have to, or features that we have to add regarding like the specific like terrain, like custom terrain, and a couple of things that now I'm blanking on. But there is a long list of features like that will be that now are fairly simple to do. We just need the time power to actually start implementing them one by one. But yeah, Marcelo, you want to take the other question?
Yeah, I'm gonna start by answering the second question, the geometry for the trees. Actually, by choosing the technique of doing a single mesh was mainly to avoid like collisions between trees that geometries that are too close. That in real life it works like no problem, but if geometries intersect as a separate meshes, then the meshing process from the solver will not work as expected. So there will be a lot of conflict edges. I think that it may work like perfectly if there are independent tree geometries, but enough separated from each other so there are not collisions between them. But because we're testing like in the first place for a more optimal input geometry, a single mesh will be mostly always the most optimal input to be working with. And second, to then, as I said, to avoid the collisions and have like the more clean possible input geometry before beginning the process. And for the multi-building materials, I think that Gonzalo, you can help me a little bit on this one because it's more like.
Yeah, we have been looking. There was two ways we were envisioning to add because right now the solver only works with the one type of building material, which adds that to all the buildings. So the two ways we were talking with Sina about this, how we could add multiple materials. One is adding like another whole like region, and the other one is just modifying. There's a particular file which assigns to like a cell sunset a particular material, and we know that the second one is the latter is the one that we should use. And it's not a difficult thing to do in OpenFOAM, but we need to design is a way for the user to specify, let's say, different type of layers of materials into each building. It's just more like a user interface thing we had to make. So we have the capability to that in a fairly straightforward way. I think that so yeah, that might be like the next feature coming up when we have some time to actually put on this. Yeah.
Yeah, Tyrone, this might be something we might want to discuss at some point, how we can best handle that in Grasshopper from a UI perspective. But yeah, that's something on the to-do list. Okay, we're already running a bit behind, as always, of course. Let's move into the contributions by Chinmay and Shruti, who did their capstone semester capstone projects on sub-issues related to this project. So I believe Chinmay is the next one here. Please take it away.
Hi, hello everyone. So my topic will be focusing on influence of vegetation structure on the urban microclimate. Next. So as we all know that vegetation definitely has its impact, but to what extent? There are many studies which have shown that it can cool down the temperature up to 15 degrees Celsius in vegetated areas compared to non-vegetated areas. But is it only about the shading? Because even the other structures provide shading. Next. So this all happens with the vegetation being present in that particular area. Many studies suggest a better UTCI results when there were vegetations in the simulation, as well as the ground surface temperatures were also reduced when it was studied with vegetation and without vegetation. Next, please. This whole thing is about the process of cooling, and this happens when the long wave radiation is kind of absorbed by the tree, and it interacts with the surrounding air temperature in terms of the heat transfer through evapotranspiration. And next, please. What are the benefits of these vegetations? Are that it not only just cools down the temperature below the canopy, but it also has an effect up to 27 meters, as per few studies, beyond the park boundaries. Next, please. Next. So we have identified there are like at least 6 levels or the stages where it affects or contributes towards cooling the temperature down due to the vegetation. For this study, I'll be focusing on the pedestrian and the tree canopy level, and specifically on how different sizes of red maple tree, which is a species that a tree type that I'll be studying for this this particular topic, is how different sizes affect on the vegetation cooling and how it's its influence on that. Next, please. So in all of these, the density of the foliage is one of the very crucial factor, which is also called as leaf area density. In this leaf area density is basically about how much leaves are present in 1 cubic meter of space of volume. And these every leaves have a small pores called stomata, which are essential for this cooling process. How does that happen is due to the vapor pressure deficit and the hot air surrounding the leaf, and the leaf get triggered, and it therefore starts the whole process of evapotranspiration and releases certain water vapor into the atmosphere, cooling down the temperature. So when I say stomatal resistance further, it all relates to this particular point. Next, please. But all of these are very sensitive to higher CO2 levels, to places which are on higher latitudes, and of course the monotonous skyline. All of these are based on certain studies, existing studies done on this particular topic. But what benefits it is, let's say, higher rain or good groundwater, good LAD values, LAD as I just mentioned, and different height variations. Next, please. So in this study, as explained by Gonzalo and Marcelo, I'll be using this solver where it takes the vegetation parameter inputs. All these vegetation parameters, there are 16 of those which affect the whole simulation pattern. And it is categorized in stomatal resistance, canopy structure, turbulence, and radiation energy. There are multiple other parameters into it, but as we can see in the next slide, that we try to identify the values that will be used as inputs and what their units are. And in this whole quest, we definitely found great data to actually use specifically for red maple. All my study is kind of using just one species right now. Next, please. So I'll be doing the 3 iterations. In all of these 3 iterations, there are certain parameters whose values will be changing. For example, tree height, LAD, leaf length, and minimum stomatal resistance. Wind speed is kept constant for all of these iterations. At the end, I'll be giving a comparative analysis without a tree iteration, as well as with one more in different month and with longer duration. Next, please. So starting off with the first iteration, the whole format, the whole layout of these iterations will be similar henceforth. It is all about understanding and analyzing temperature, moisture content, relative humidity, stomatal resistance, and leaf temperature, because all of these factors have a potential on cooling down the temperature. As we can see here, there is a graph in center which also discusses about how the temperatures grow, or the range of the temperature is growing as per the time in elapses, and the month of this particular simulation is June, mid-June, for in fact all the simulations, and the time period is from 11 a.m. to 4 p.m. Next, please. We'll keep the time into the picture because this affects the whole study, as the stomatal resistance and leaf temperature, as seen on the left side in the GIFs, is all the 5-hour time lapse of it. And we can see that as the leaf temperature increases, the stomatal resistance also increases, but it is not uniform. This relation also is dependent on the time that we are trying to study this particular factor. Next, please. When moving forward with moisture content and relative humidity, there is an interesting phenomena happening here, is that usually for cooling temperature down, we need the moisture content increasing as well as the relative humidity also going up. But in certain cases, that's not happening. It's kind of inversely proportional to each other. And this phenomena usually happens, as per National Weather Services, whenever the air temperature is still hot. So in that cases, the relative humidity will drop and will not increase. And you can also see on the graph, the dotted lines suggest the drastic change and the inverse proportionality of moisture content and relative humidity. Next, please. When we analyze all three of them together, the temperature, moisture content, and relative humidity, this particular iteration with tree height of 3 meters, as you can see on the top, the LED values and all the leaf lengths, we identified that smaller trees are kind of getting adversely affected with, let's say, harsh environment outside, because it is June and it is from 11 a.m. to 4 p.m. It is kind of not helping the tree to cooling down the temperature. Next, please. In this particular iteration, we can see the tree height is increased to 7 meters. The rest everything is same. We can see the temperatures getting changed and how the wind velocity is also affecting this temperature. Next, please. In this, it is a similar pattern like earlier. The stomatal resistance gets increased with leaf temperature. But mind you, this particular analysis, the plane of analysis, is at the center of the crown of the tree. So it changes as per the tree height. And I've kept it that ways in order to study the stomatal resistance and leaf temperature to the core, because at the crown, it is much more than what it is below the ground. So what I've interestingly identified is that the stomatal resistance values or the leaf temperature is not related to the tree size, because it is just for the leaf. And therefore, we can see some similar values for this iteration and with the smaller trees as well. I'll just highlight a number of stomatal resistance. Right now, the higher number is 4,500. Earlier, it was 2,400. And we can see how it relates further. Next, please. Now, again, the same story happens with the moisture content and relative humidity. But here we can see that the circle at the bottom of the graph 10 can tell you that there is a slight deviation at relative humidity, which suggests that the steep drop of relative humidity is kind of getting plateaued, which is what suggests or highlights that we are going more towards the cooling potential, as in when we are increasing the tree height or we are increasing the leaf length or LED values. Also, not to forget that the larger the tree, it has more impact on its surroundings, as we can see on the moisture content on the left side. The red marks are getting more wider as the tree is getting larger. Next, please. Again, the comparative analysis with all three, temperature, moisture, and relative. If you see the mark A and mark B, we can definitely conclude that the places very near to the trees, for example, relative humidity, are getting higher. My apologies, the mark is getting on to the numbers, but you can be assured that the numbers are getting increased as compared to other iterations. And as and when we go away from the tree, even in the same plane, in that drag effect, it's kind of the relative humidity is not increasing that much as it is increasing near the tree. Next, please. Now, the iteration 3 is with 14 meters of tree height. So there were 3 tree heights, 3 meters, 7 meters, and 14 meters. For 14 meters, initially everything looks fine and similar, because all the temperatures are around 26 to 29 degrees Celsius or 79 to 88 Fahrenheit. Next, please. But it's interesting to see that stomatal resistance and leaf temperature in here is matching with the 3 meters one. So as you can see, the highest stomatal resistance here is 2,400, as I mentioned earlier, was also of the 3 meter tree. And this is because I think of the minimum stomatal resistance input that we gave to the solver. And of course, the leaf length and the LED values that we are trying to put in. It's very interesting to study this, because as and when we go forward, there are multiple numbers that can be studied. And also in this, the graph 12 shows a very subtle way of changing stromatic resistance and not a drastic way. Next, please. Here, the moisture content and relative humidity is much better than the earlier two again. Now you can see that there are not many drastical changes in the graph as opposed to the 3-meter height of a tree. This also suggests that larger the tree, it has more impact on the cooling potential. Next, please. Again, the same thing, but here I identified a point below a tree canopy and one above it. So it is pretty evident that the air temperatures, the relative humidity, everything is better below the canopy as opposed to above the canopy. Next, please. Now, this iteration, till now, what we have identified is not actually cooling down the temperature. Everything that we are seeing is kind of still getting where the air temperature is higher because relative humidity is not getting that lower. So I wondered why it's happening. Because the solver is performing perfectly fine. Even the trees being there has some effect on it. So I tried this and saw that when I put one tree instead of so many that we saw earlier, next, we can see that it actually doesn't change anything. There are no much variations. It's just where the tree is, you can see the drag effect happening and other numbers are changing here and there. So it's kind of like a desert situation sort of a thing where not much is changing in terms of the air atmosphere or the relative humidity. Next, please. And finally, what I tried to do is I changed the month, keeping all the parameters same for the 7-meter height iteration, and also the duration of the time, which is now from 11 a.m. to 7 p.m. In here, it was very interesting because we can see the relative humidity is shooting up to 70% almost. And in fact, moisture is also increasing. So now we are getting there where we actually wanted to go, is that where moisture is increasing and relative humidity is increasing. This is just one of the factors which I'm focusing on for the trees, which is essential for cooling down the temperature. Next, please. And these are the graphs which show the perfect change for stromatic resistance getting decreased, relative humidity is increasing, as well as the air temperature is dropping down. So it's very interesting to study that. It definitely tells us that which month you're studying, and it's not about 1 or 2 hours, but it's definitely about the whole day or maybe like multiple hours that you'll kind of study and then try to identify how that affects the cooling potential. Of course, the air temperature in March also goes down as we go to the 7 p.m. mark, but it is much better than what we saw for the June month. Next, please. So actually also like just for the reference, I've shown here how June and March are for the dry bulb temperature are so different, like it's 94 and it's 80. So sometimes more harsh temperatures can get like adverse on or cannot help the trees to cool down the temperature. Next, please. And lastly, these are the 32 iterations, the ones that I just showed about all the inputs, the parameters and their combinations. This was done by design of experiments in JUMP. And the next step would be to study as much as simulations as possible. I've done 32 till now, more than, in fact, more close to 50, but I would love to do more in different month and different timings, and then find out what their outputs are to have a more comprehensive analysis on the same. And yeah, thank you for this. And before just ending, I would quickly like to thank Gonzalo for this tool and Marcelo for helping me out, and Ray and Shruti for always being there with the capstone discussions, and not to mention Patrick, Professor Kastner. Actually, he has helped me throughout all of these things and understood all my concerns and queries, and Professor Marshall as well. He also entertained us in their office. I think we're missing Professor Rakha here, but thank you to him as well for his continued support, and not to mention Sina as well. Thank you.
Well, Chime, great stuff. Shruti, maybe I know we're over time, but maybe there might be, maybe Tyrone, you might, if somebody needs to go, by the way, it's okay. This is recorded. I'll send it around. But if there's a pressing question, I want to give the opportunity maybe to get one or two in while we're on this topic. I think Tyrone was very interested in vegetation, right? Specifically, Marcelo's also on the call. The other Marcelo, Kirksville Marcelo. Just in case there's anything, maybe we can
Thank
have.
you, Patrick. I have like a I don't know, simple question. I mean, first of all, it's very impressive the progress the whole team has made during the last month and a half. Probably that was the last time I had the chance to review. Regarding the impact and the effectiveness of trees, I have, let's say, two questions. One is about the typical question in this case is about validation. I'm aware that SINA have been working on the validation component of this problem. So what you have here is Chinmay is pretty sophisticated in terms of the description of the tree. So we have 16 parameters, if I'm not wrong. I mean, in the everyday work at a design firm, the parameter is the number of trees, the type of tree, and the age, which is related to the size, which is also related to maintenance and price, right? So 3 basic parameters, you have 16, right? So in your opinion, let's assuming that at some point you will do the validation of all of this. Do you see any, let's say, general parameter, like a general proxy parameter? For example, when we do daylighting has every single hour of the year, minute by minute, if you like. But at the end of the day, we say, 50% of the time you are within the comfort zone. Okay, you're good to go. You don't worry too much about all the little details, but you're targeting the core of the problem. It's a very mature metric, the one I'm talking about. Do you see any possibility to visualize this general proxy that can give a sense of direction to designers to make decisions about this?
Yeah, yes, that's a great question. Absolutely. In order to use it in a day-to-day life or for designers, I'm pretty sure no one is going to use all the 16 parameters and change them. So having said that, we can definitely compartmentalize it by saying as per the region, as per the tree height, because right now what we did with design of experiments is that it's kind of also changing the tree leaf length with the tree size. So in real life scenario, if we just try to identify how the tree grows, sometimes it's a constant process where we can understand that a certain tree leaf length and certain tree size with stomatal resistance are pretty much same. So we can definitely say, let's say A, B, and C are the inputs, and that's it. So if you want to use, let's say, different types of trees, as per the month, we can use them for that particular compartmentalization. I feel that this can be done back end and can be just explained to the designers that if you want to use this for this month, this particular tree, just use A or B or C. Very easy to easy to say than actually to be done, but I feel that we can definitely use it in that ways, because there are not all 16 parameters are not essentially necessary to take into consideration for a general analysis for the urban designer or planning situation. So yeah, I think we can definitely do that. More detailed analysis is necessary for that.
Thanks for me. There's one more from Tyrone. Maybe we can do a second. Then we have to move on.
I think Chinmay's just identified something. There's a lot of space here for work, future work. And to Marcelo, to your question, I think it's not gonna be a simple question, like I think in terms of, what kind of tree, what species, and time. I think it's kind of more what Chinmay talked about. But I think what we'll have to figure out is that there's a translation, right? So he's talking about stomatal resistance, leaf, length, and there's going to be this kind of translation that we're going to have to do. But my thing is, I think designers need to come up to the plate and update their knowledge and really kind of understand stomatal resistance, because if you looked at the presentation, that's what's causing the cooling to happen around this tree. And to me, it looks like little vents, right? Little vents that release moisture vapor, right? It's how this tree actually does its job. So for me, I'm going to push our designers. They're going to need to learn a little bit more about what these trees are actually doing, so that we actually understand when we design, what's the right kind of thinking to kind of give in terms of what we're going to do in terms of our intention. But I think what he's found is I think it's going in the right direction. I think there's still some more work to do, but I think we're going to have to ask our designers to they're going to step up to the plate. I think here they've got to learn more about this process. And I think his work is going to open that up a little bit more in terms of their education. So we may have to invite Chinmay and give some special talks on some matter of existence and some of the work that he's figured out here. I think that's probably, in my mind, where I think some of this is probably headed. And I hope that he finds that interesting, because you probably can do some YouTube videos on this in terms of education and whatnot, in terms of where this goes in the future. But no, thank you.
Thank you, Darren. Yeah, absolutely. I'm
Thanks,
happy to.
Yeah, Chinmay's graduating soon. Just saying. So if there's any need at Ferguson, well, I'm sure he'd be interested in
100%.
any sort of form of engagement there.
Sure. Thanks, Patrick. Yeah.
Let's talk offline. Let's try to figure out question or response.
Okay, thanks everyone for sticking around. So last contribution. So Shruti thought a lot about how we can turn these cases that we've seen that are sort of toy cases, right? Where it's like a idealized building canyon with a couple of trees in the front. How do we apply this to actual cities? And how can we maybe build a repository of test cases in canonical city typologies or urban typologies that we can maybe pull from if there's a question or if there's a new development, let's say in a desert climate or in another type of climate, right? Like what would be an urban morphology that we can pull from and sort of test some of these, how do we say, interventions, vegetation related interventions. And so I'm not going to speak any longer, but Shruti looked at, I believe, 12 different urban typologies. And originally we wanted to simulate them all, but the tool wasn't there at the right time. But we have completed all the urban geometries as I understand it currently. And so hopefully in the future we can use them to build these test cases, simulate them, and then have a public repository of the results then in the future. So Shruti, please take it away. Thank you.
Thank you, Patrick, for the introduction. So hi, and I basically worked on developing canonical geometries to evaluate microclimate impact for our tool. Next. So to begin with, we are all familiar with the concept of urban heat island effects, where basically cities experience slightly higher temperatures compared to their surrounding rural areas. So these urban zones basically contribute to over 70% of global energy consumption, largely driven by the microclimatic conditions prevalent in the city. Next, so urban heat island effect impacts us across various scales. On a micro scale, they drive up the energy demand as city temperature can rise by 1 to 7%, leading to increased cooling needs. Gonzalo, if you can press next. This effect also degrades air quality, intensifying the formation of ground level ozone, because even 1% increase in temperature can shoot up ozone level by 5 to 10%. And this is directly proportional to increasing economic costs to like heat the buildings, cool the buildings. Next. So at the meso scale, which is basically our neighborhoods and communities, the impact of urban heat island effect is like more localized. So where we say there's disproportionate heat stress. So neighborhoods which have more vegetation versus neighborhood which don't have a lot of vegetation, the temperature difference is between 3 to 5%. So low-income households which do not have access to that many green spaces, which are on the outskirts majorly, experience a bit higher temperatures. Next. Next. Yeah. So at the micro scale, which is basically our pedestrian level, which we don't talk about often, is in this climate, it's pretty difficult to walk, and it actually causes behavioral impact. So people don't prefer walking, prefer taking their car, because the streets out there are too hot for them to be walking comfortably. Next. So this phenomenon definitely raises concerns for researchers and urban designers, emphasizing the urgency of addressing this issue. So in today's practice, we definitely use a lot of simulation tools. Yeah, we definitely use a lot of simulations tools to understand how to design our cities and how to go about our urban practice. So the traditional approach is basically where we use an EPW file and see where the sun direction is, how the wind direction is, to basically conceptualize our design. Although it's easy to access and it's time efficient and used by preliminary design. Next. What it fails to address is what happens at the ground level or at the pedestrian level. So basically, this data is very generalized and lacks precision and cannot calculate for extreme weather conditions. Next. So the question is it the buildings or the planning? Next. So this is where canonical geometries actually come in picture. So basically, these geometries are done through like thorough research as to how cities were developed, how urban design started, and how it's still in practice to create this set of repository where we can basically like pick this grid up, put it on our site, check how the microclimatic situation is there in that particular weather climate, depending on how city was designed or how we want to design it, see how the microclimatic situations are, make a little bit iteration, and I mean, at a very early stage, we get a good idea as to how we should go about the conceptualization of the design. So first, because they're like standard 12 repositories, we have consistency throughout, and we can make rapid decisions, and we can scale them and adapt different solutions and iterations to see what fits best. Next. Yeah, so if you see, this is basically the geometry that I'm going with, which is a 4x3 grid, which is suitable for large. We can scale it if we want large scale urban projects, or just like omit blocks if we want to see what happens at the smaller scale. So it's efficient. It's efficient because it's faster to set up and reduce computational load, because the end goal is obviously to like have these pre-simulated, so you just like instantly get an idea as to what's happening. Scalability and global relevance, because the typologies that were studied across the globe, and different typologies, so you can just have like a bigger picture of what's happening everywhere. Next. So now when I was like thinking and studying as to what typology or what cities or what geometries I actually need, I had to like dive into the base of what affects the urban microclimate. So first was street. The orientation of street affects wind flow, solar axis, and heat distribution. The blocks, depending on their layout and size, affects the same buildings because of their height, design, proportion, and placement, can affect microclimate as it can trap heat or otherwise. And then public spaces, because of evapotranspiration, we can have a bit cooler environment and see how it affects. Next. So besides that, there were like more technicalities that I wanted to explore and have in my canonical geometries in general, that I cover everything. So we have like a whole set of cases, different cases of things that can affect the microclimate potentially in our design. So first was the standard deviation of building heights, as in we know that tall buildings channelize wind effectively. And also if we have like narrow streets, it can create heat, and it can trap heat. Similarly, the distance between buildings. Next. So aspect ratio, which is the width of the street to the heights of the building around. We want to know if the air's like rising up or it's trapped because the streets are very narrow. And then the sky view factor, which is basically once you are at the ground, how much sky is visible. So to understand radiative cooling and heat loss and thermal comfort. Next. So vegetation, because obviously, like I said, it helps naturally cool the environment and improve vegetation. Besides, also porosity of materials with high albedo trap a lot of heat, and materials with less albedo help like not absorb heat as much. So yeah, I wanted to study them also. These are basically the parameters that I went by to select my geometries. Next. Can you play that video? Yeah. So we know that cities have evolved over time, and they started either radially or rectilinear fashion. So I wanted to carry how cities evolved, and these grids, which are like fixed at this point in urban design, and see if at least at this point we want to go with this grid or we want to go with this typology. So we get a big repository of every kind of urban design and practice right now. So like suppose say rectilinear. So I chose two case studies for rectilinear, which was Belo Horizonte, Brazil, and Chicago. So if you see, if you know that Chicago is like east to west orientation, where if you see we have skyscrapers and the streets are comparatively narrower. So we know for a fact that it will accumulate heat and the building. My bad. And so the height of the buildings is different. Next. Yeah. So these, even the site that was selected for this is such that we have like different zones in that one geometry, which is like we have our commercial spaces, we have residential spaces, and we have green zones as well. So we can basically simulate everything. Next. The geometries were selected as to we get a bigger scale of height deviations. Next. And we have like difference in the distance of the distance between nearby buildings. Next. Aspect ratios and again sky view factor and vegetation cover. So all these geometries were selected, which actually gives us a diverse picture about all these factors that affect the microclimate. Next. So same with Belo Horizonte, Brazil, which is the streets were designed north to south, which is actually good for reducing heat islands. So we have like comparison of type A versus type B. Next. Similar with radial grid, Amsterdam basically has so basically this grid that was selected is next to a water body, so it will be good to understand how it minimizes heat, and the buildings we know are like not that tall in height, but we have like wider streets. Next. So if you see this is my geometry for Amsterdam, which is where the radial grid started, so it'll be interesting to see how it works out. Next. So with Doha, Qatar, where it was relatively hotter climate, so to see that difference would be nicer. And also Doha, basically, if you see the grid for Amsterdam was like more perfectly radial, whereas Doha also started growing organically within the radial grid. Next. So yeah, so similarly, I have created this whole repository of 12 geometries around different urban typologies like rectilinear, radial, organic, checkerboard, and hybrid, which more or less covers the whole urban design and practice right now. And every geometry, if you see, has a different reason from the above to be selected. And yeah. So for future studies, once we have this tool developed, I hope that we could run all these 12 through simulation. So we basically have pre-simulated geometries. So for urban designers and researchers, it will be like extremely easy. You just have to click and you know how it will work in your temperature. You can make tiny bits of iterations and see, and then move to your design. And next. And thank you.